Hey guys, this is Jimmy Wong from Planning Things Tutoring. In this video, we'll go over permutations and combinations and how they're different from one another. Don't forget to use my referral code JimmyMon20 to get 10% off your next tutoring package. All right, let's just get straight to the point right away. In permutations, the order matters. Order matters for permutations. Whereas for combinations, order does not matter. Now, you may have heard this phrase numerous times, and you're probably going to hear this countless amount of times after this as well. But you still may not have a great clue or not a great understanding of what that exactly means. Well, all this means is, let's use like a real life example. So whenever we have, in our daily life, we tend to use numerous devices which tend to be password protected. For example, many phones tend to have either like a 4, 6, or even like an alphanumeric lock, different kinds of passcodes. And let's just use a case where we have a phone with a 4-digit lock. There are 4 digits which make up this lock. Well, there are a total of 10 numbers that we can use, 10 digits that we can use. We can use any combinations of these 10. Well, if this password was made out of based off of permutations, let's say that the password is 3584. Well, in that case, the only way to open this phone through the password itself is by typing 3584, at least if it were based off from permutations. Whereas if it were based on combinations, any arrangement of the numbers 3, 5, 8, and 4 would work fine. For example, a number like 4358 would work just as fine as 3584. So what this means is the order of which each of these the order of which each of these objects, I guess in this case we just have numbers as our objects, do matter for permutation, whereas for a combination it doesn't really matter at all as long as you're using the same ones. So as long as you're using 3, 5, 8, and 4, any combination of those 4 numbers would work for a combination-based problem, whereas for permutations, you do need 3, 5, 8, and 4 in that specific order. In general, if the question is asking for the number of arrangements in a position-based group, or as in like if it's like first, second, third, maybe like a president, vice president, etc. A position-based group, a password or letter arrangements in a word, all these kinds of examples tend to be permutations. Whereas a combination would be found in questions which tend to refer to committees or groups that don't really have a particular position. And they also refer to things like toppings on. A question about combinations tend to have things like tend to be about things like toppings on a pizza or maybe toppings on ice cream, etc. Now, there are a few different ways to represent a permutations. In general, we can use N, P, R, or P, N, comma, R. Both of these are both symbols for permutations, and this just means that there are a number of ways. I mean, the permutation just means the number of ways. The number of ways is selecting R objects, R number of objects, and assign them to R different kinds of jobs from a total of N different objects. So let's say that you have maybe 10 jobs or something, and there are 10 people. Well, in that case, you would be assigning those 10 people to those 10 jobs in a particular way. That would be a permutation. Whereas in a combination, and the general formula for permutation, by the way, is n factorial divided by r fact. I'm sorry, n minus r factorial. N minus r factorial. Yeah. This is what NPR is equal to. So let's just put this out to test with a couple of word problems, I guess. So let's say there are 6 different openings at a certain company and a total of 10 applicants that applied for those jobs. How many different ways can you assign these 6 jobs to the applicants themselves? Well, what we first need to do is we need to recognize that there are 10 different possible ways, there are 10 different possible people that are available for each of these jobs. Well, let's say this is job 1 right here, job 2, job 3, job 4, job 5, and job 6. There aren't any more jobs than those 6 jobs, but for the first jobs, for the first job, there are 10 people available, persons 1 through 10. All 10 of them are available for the first job. Now for the second job, 1 person has already been taken away for the first job, so now there are only 9 people left. And we keep on going, and we just end up multiplying each of these values, and we get a number which is the number of the total number of permutations, or the total number of ways that a person, or that 10 different applicants can apply for these 6 different jobs. Now this is the same thing as saying NPR is equal to n factorial over r factorial. Well, in this case, n factorial is just equal to 10 factorial, and r factorial, or n minus r factorial, is the same thing as saying 6, or 10 minus 6 factorial. 10 minus 6 factorial, which is the same thing as saying 10 factorial over factorial. Well, 10 factorial is equal to 10 times 9 times 8. 7 times 6 times 5 times 4 times 3 times 2 times 1, whereas 4 factorial is equal to 4 times 3 times 2 times 1. Well, 4 times 3 to 1 is on the top and on the bottom, so you just cancel them out. And now we're just left with 10 through 5, which is exactly what we got here. All right, so when we do this, we get 151,200 total different ways. 200 different ways that you can assign those 6 jobs to the applicants. Now let's see. How many distinct 11-letter arrangements can be found in the word Mississippi? Now, by letter arrangements, that just means that you can you're just rearranging the word into different words, I guess. M, or I, M, S, 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 I, P, P, I would work as an example of a different rearrangement of this word. Even though this is not a real word itself, this still works as a rearrangement of the letters, as long as you're using all 11 letters. Now, the reason as to why I highlighted, or I underlined distinct, is because there is no difference between this and if I were to switch out these 2 S's and I were to get M, I, S, S, I, S, S, I, P, P, I. There is no difference between these two words, yet between these two letter arrangements. Yet S and S were supposed to be flipped, and therefore it wouldn't really make sense to count those as separate permutations. Well, we know that this is also be a permutation, but now we have a total number of letters that we have is 11. That's going to be the total number of objects that we have. It's going to be 11 factorial. Now, another way you could have wrote this formula, instead of writing it as just n factorial over n or n minus r factorial, could have written also as n factorial divided by n1 factorial times n2 factorial dot dot dot. Now, what do these n1, n2s, etc. mean? Well, these just stand for specific subsets or specific groups within the larger group of the n, which keep being repeated. So this tends to be used for the letter arrangement type problems. So here, as we can see, the letters I and S are being repeated 4 separate times. And the letter P is being repeated 2 times. Well, to avoid getting the same word over and over again, we can divide out the different arrangements of the S's, the P's, and the I's whenever they're switching themselves around within themselves. And that's by dividing out the 4 factorial for the S, the 4 factorial for the I, and the 2 factorial for the P. And this leaves us with 34,650 total different distinct 11 letter arrangements that can be formed from the word Mississippi. Now let's focus on combinations. Combinations just refer to the number of ways that you can select R amount of objects from a total of n number of objects, which tends to be represented as NCR or N choose R. And this can also be represented in a different format. It's called the more sort of the binomial type format, more so used in probability. Well, what this says is that this gives you the number of ways that you can select R amount of objects from a total of n number of objects. So let's also work on a couple of problems based off of this as well. Just a reminder, just a note, the general formula for this is NCR is equal to, this is equal to n factorial over n minus r factorial times r factorial. Now let's work on the few problems. Let's say 17 people were eligible to be in a particular committee. How many different committees can be formed, and the committee is to be made out of 13 people? Well, remember, in a committee, there are no most important position or least important position. We're just adding people to the committee itself. Any 3 people could be selected to the committee. Doesn't matter which order it is that they were selected into the committee. And so in this case, we would just be using 17 choose 3. Well, this would be the same thing as saying which is equal to 17 factorial over 17 minus 3 factorial, which is 14 factorial, times 3 factorial. And this gives us a value of 680 total number of possible ways that you can form a committee made of 3 people. Now let's say that the same 17 people belong to a seminar course, and this course consists of 4 separate lectures and 13 students. If the committee has to be built by 2 students in 1 lecture, how many combinations are now possible? Well, now we're actually repeating some things. So we would need to use this new formula we worked on when we did the problem on the Mississippi. And that's going to come down to being using the n factorial and the subsets of n factorials. Well, it's a little bit different when it comes to combinations. When we're working with combinations, we would have a combination for each separate group. So there's a combination for the lectures. You're choosing 1 lecture out of the 4 people. And there's a different set for the students. It's going to be, you're choosing 2 students from 13. And this gives us a value of another way that you could have done this is just, if you're representing it in this way, this is the same thing as just saying 4 factorial over 4 factorial times 1 factorial multiplied by 13 choose 2, which is 13 factorial over 11 factorial times 2 factorial. And this is equal to 312 total different combinations. For combinations, a rule to recognize, remember all the time, is n choose r is always equal to n choose n minus r. This means that 13 choose 2 is the same thing as 13 choose 11. And there's actually a pretty nice way of finding the value of certain combinations without really using a calculator, nor actually working it out using the factorial method or the formula we kind of looked at earlier. And this is by using Pascal's triangle. So Pascal's triangle is just how we can use Pascal's triangle to find out the certain values combinations is actually that you can look at the value of these numbers and they would tell you the number of combinations for a particular number of a particular numerical value of n. So let's say that you were doing 1 choose 1. Well, in that case, we have so what this Pascal's triangle tells us is for each value, this is going to be 0 choose 0. How many ways can we select 0 objects from 0 objects? Well, there's only one way, and that's not picking it up at all. Now, the second option is the second level is when we have 1 object in total. Here you're choosing out of 1 object, you're choosing 0 objects, and the other option, you're selecting one object from a total of one object. Here we have m choose 1, which is 2 choose 1, or 2 choose 0, 2 choose 1, and 2 choose 2. As you can see right here, 2 choose 0 and 2 choose 2 are both equivalent, which continues to satisfy the idea that n over r is equal to n over n minus r. If we keep this going, we get that this one is equal to 3 choose 0. This is 3 choose 1, 3 choose 2, 3, 3. And this continues to go on forever. All right. I hope you guys learned something new from this video, and thank you all for watching.